Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something extraordinary surrounds you. A substance so common you barely notice it, yet so remarkable that without it, no life could exist. Water. It falls from the sky, carves through mountains, and flows through every cell of your body. It is the only substance on Earth that exists naturally as solid, liquid, and gas at the same time. This is water, the molecule that makes life possible. A simple union of hydrogen and oxygen that has shaped continents, filled oceans, and sustained every living thing since the first cells formed billions of years ago. Tonight, we journey into the quiet wonder of water. We will explore over 100 soothing facts about this extraordinary substance, from its cosmic origins in dying stars to the hidden oceans beneath the moons of distant planets, from the snowflakes that fall in perfect hexagons to the ancient water molecules that now flow through your veins. There is no test at the end, no rush, no urgency, just the gentle unfolding of water's endless story to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and allow yourself to drift into the peaceful flow of the world's most essential substance. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable processes that sustain our world. Either way, this space is for you. There is something deeply calming about contemplating the quiet journey of water. Every raindrop, every wave, every breath of mist carries within it a story billions of years in the making. You are connected to this story more than you might realize. The same water that fills the oceans also flows through your blood. The same hydrogen atoms that formed in the first moments after the Big Bang now help carry oxygen to your brain. You are, in a very real sense, made of ancient starlight and water. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let the weight of the day drift away, and let us begin with the first of many quiet truths about water. Water is patient beyond measure. It wears down mountains grain by grain. It carves canyons over millions of years. It waits frozen in glaciers for millennia before flowing again as streams. And yet, within all that slowness, there is constant motion, molecules vibrating trillions of times per second, hydrogen bonds forming and breaking in an endless dance, currents circling the globe in patterns that shape the weather of continents. Tonight, we will wander through this magnificent liquid world. We will meet the molecules that make up every ocean and every tear. We will discover the strange properties that allow life to exist. And we will uncover truths about water that may surprise even the most curious minds. But there is no hurry. Water has been circling this planet for 4 billion years. It can continue its quiet journey while you rest. Let us begin with where water comes from. Hydrogen atoms in water were created moments after the Big Bang. Every hydrogen atom in the glass of water beside your bed has been around since near the very beginning of time. In the first few minutes after the Big Bang, the universe was a seething cauldron of energy so intense that particles could barely hold together. As temperatures dropped just enough, protons and electrons settled into the simplest of atoms, hydrogen. These were the first atoms to exist, born from the cooling embers of creation itself. No star had yet ignited. No planet had yet formed. There was only hydrogen, drifting through an expanding void of unimaginable scale. Billions of years later, those same atoms found their way into molecules of water on a small blue planet. So when you take a sip of water, you are quite literally touching something that has existed for nearly 14 billion years. It is one of the oldest materials you will ever hold. Oxygen atoms were forged inside dying stars. Unlike hydrogen, which formed in the earliest moments of the cosmos, oxygen took much longer to appear. It was created deep inside massive stars, where temperatures reached millions of degrees and atoms were fused together under crushing pressure. When those stars exhausted their fuel and collapsed, they exploded as supernovae, scattering newly forged elements across the galaxy. Oxygen was among the most abundant of these stellar gifts. Slowly, over billions of years, that oxygen drifted through space, mingling with hydrogen in vast interstellar clouds. The oxygen in every molecule of water you have ever tasted was once part of a star that no longer exists. It is a gentle reminder that destruction and creation are deeply intertwined in our universe. The very breath you take and the water you drink carry within them the remains of stars that burned out long before our sun was born. Water molecules first formed on dust grains in interstellar space. Long before the Earth existed, water molecules were quietly assembling in the cold, dark reaches of space. On the surfaces of tiny dust grains drifting between the stars, hydrogen and oxygen atoms met and bonded in temperatures close to absolute zero. These microscopic grains acted as gentle meeting places, allowing atoms to slow down and stick together in ways that would be impossible in open space. Over millions of years, layers of water ice built up on these particles, forming thin frozen coatings no thicker than a few molecules. Eventually, these icy grains gathered in vast molecular clouds, the same clouds that would one day collapse to form new stars and planets. Some of those ancient water molecules survived the turbulent birth of our solar system and found their way to Earth. It is a quiet thought that the water flowing through rivers today may trace its origins to a single dust grain drifting in darkness billions of years ago. Much of Earth's water arrived aboard ancient comets and asteroids. When the Earth first formed roughly 4.5 billion years ago, its surface was a molten sea of rock, far too hot for liquid water to exist. The water that now fills oceans, rivers, and clouds was delivered later, carried by comets and asteroids that bombarded the young planet over hundreds of millions of years. These icy visitors had gathered water in the outer reaches of the solar system, where temperatures were low enough for ice to survive. As they collided with Earth, they released their frozen cargo, gradually building up the water that would become home to all life. Scientists have confirmed this by comparing the chemical signatures of water in comets with water on Earth and finding close matches. It is humbling to think that every raindrop owes its existence to collisions that shook the planet in its earliest days. The oceans beneath tonight's sky are, in a sense, gifts from space. Comets are often called dirty snowballs of frozen water and dust. Comets are among the most ancient objects in the solar system, leftover fragments from the time when the planets were still forming. They are made primarily of water ice mixed with dust, rock, and frozen gases, earning them the affectionate nickname of dirty snowballs. When a comet drifts close to the sun, the heat begins to vaporize its icy surface, creating a glowing tail that can stretch for millions of kilometers. That tail is mostly water vapor and dust, gently streaming away from the comet under the pressure of sunlight. Despite their spectacular appearance, comets are usually quite small, often only a few kilometers across. Yet these modest bodies carry within them a record of the early solar system, frozen in time for billions of years. Watching a comet cross the night sky is like glimpsing a traveler from the very dawn of our planetary neighborhood, drifting quietly through the darkness, carrying water from another age. Some meteorites still contain water locked within their minerals. Not all water from space arrives as ice on the surface of comets. Some of it is hidden away inside the crystal structures of minerals within meteorites. These rocks, which have traveled through space for millions or even billions of years, occasionally contain tiny amounts of water trapped when the minerals first formed. Scientists have discovered water molecules bound within the lattices of certain meteorites, particularly a type called carbonaceous chondrites. By carefully heating these samples in laboratories, researchers can release the water and study its chemical fingerprint. The isotopic ratios of hydrogen in this water help scientists trace where Earth's oceans originally came from. It is a remarkable thought that a small rock sitting in a museum display case might contain water older than the Earth itself. These meteorites serve as quiet messengers, carrying ancient water from the depths of the solar system right into our hands. A cloud of water vapor near a distant quasar contains more water than all of Earth's oceans combined. In the distant reaches of the universe, astronomers have discovered a reservoir of water so vast it defies ordinary imagination. Surrounding a quasar more than 12 billion light-years from Earth, a cloud of water vapor holds roughly 140 trillion times the amount of water in all of our planet's oceans. This water exists as vapor, spread thinly across a region of space hundreds of light-years wide. The quasar at its center is an enormously powerful source of energy, powered by a supermassive black hole consuming matter at a furious rate. The heat and radiation from that process are what keep the surrounding water in its gaseous state. Despite the almost inconceivable quantity, the vapor is extremely sparse by earthly standards. Yet its very existence tells us that water is not rare in the cosmos. It has been forming and gathering since the earliest epochs of the universe, quietly accumulating in places we are only now beginning to see. Water molecules drift through interstellar clouds between the stars. The space between the stars is not entirely empty. Scattered across the galaxy are enormous clouds of gas and dust known as molecular clouds, and within many of them, water molecules drift in gentle silence. These clouds can stretch across dozens of light years, containing enough material to form thousands of new stars. The water within them exists mostly as thin films of ice-coating microscopic dust grains, though some of it drifts freely as vapor in the warmer regions. Temperatures in these clouds can drop to just a few degrees above absolute zero, making them some of the coldest places in the universe. Despite this extreme cold, chemistry continues at a slow and patient pace, building up molecules one atom at a time. When parts of these clouds eventually collapse under gravity, new stars and planetary systems form, inheriting the water that accumulated over millions of years. The water on Earth almost certainly began its journey in one of these quiet interstellar nurseries. A water molecule is made of two hydrogen atoms bonded to one oxygen atom. The molecule of water is beautifully simple. It consists of just three atoms, two of hydrogen and one of oxygen, joined together by covalent bonds. In these bonds, the atoms share electrons, creating a stable union that is remarkably difficult to break apart under everyday conditions. The oxygen atom sits at the center, with the two hydrogen atoms attached at an angle, giving the molecule a slightly bent shape rather than a straight line. This arrangement is the foundation of nearly all of water's extraordinary properties. Despite its simplicity, the water molecule behaves in ways that continue to surprise scientists. It is small enough to pass through the tiniest pores in a cell membrane, yet strong enough in its bonds to require significant energy to split. The formula itself, two hydrogens and one oxygen, is probably the most famous molecular recipe in all of chemistry. And yet, from this modest combination, entire oceans, atmospheres, and living bodies are sustained. The bent shape of the molecule gives water its unusual properties. Water's remarkable behavior begins with its geometry. The two hydrogen atoms do not sit opposite each other in a straight line. Instead, they are angled at roughly 104.5 degrees, creating a bent shape that has profound consequences. This angle means that one side of the molecule carries a slight positive charge and the other a slight negative charge, making water what chemists call a polar molecule. Because of this polarity, water molecules are attracted to one another and to many other substances, which is why water is such an excellent solvent. The bent shape also contributes to hydrogen bonding, the weak but numerous attractions between neighboring molecules that give water its high boiling point, strong surface tension, and unusual density behavior. Without this particular angle, water would behave like a simple gas at room temperature, and life as we know it could not exist. A tiny bend in a tiny molecule quietly underpins the chemistry of an entire planet. Water is polar because one end is slightly positive and the other slightly negative. The secret behind so many of water's talents lies in its electrical imbalance. Because oxygen pulls on shared electrons more strongly than hydrogen does, the oxygen end of the molecule carries a slight negative charge, while the hydrogen ends carry a slight positive charge. This separation of charge is what scientists mean when they call water a polar molecule. It is not a strong charge, nothing like the jolt of static electricity, but it is enough to make water molecules cling to one another and to almost anything else they encounter. This polarity is why water dissolves salt so readily, pulling apart the ions and surrounding them in a gentle cage of molecules. It is also why water creeps up the sides of a glass tube and why a thin stream of water bends toward a charged object. Polarity turns an otherwise unremarkable liquid into the most versatile solvent on Earth. Nearly every chemical reaction inside your body relies on this quiet electrical tug. Hydrogen bonds form constantly between neighboring water molecules. Water molecules do not drift past one another in complete independence. Because of their polarity, the slightly positive hydrogen end of one molecule is attracted to the slightly negative oxygen end of its neighbor. This attraction is called a hydrogen bond, and it is one of the most important forces in all of chemistry. A single hydrogen bond is relatively weak on its own, far weaker than the covalent bonds holding a water molecule together. But in a glass of water, billions upon billions of these bonds form a constantly shifting network that gives water extraordinary strength in numbers. Hydrogen bonds are the reason water has a high boiling point, a high heat capacity, and a strong surface tension. They are also the reason ice floats and why water can climb up narrow tubes against the pull of gravity. Without hydrogen bonds, water would be a gas at room temperature, and the oceans would simply evaporate into the sky. These gentle attractions quietly hold the liquid world together. These bonds break and reform trillions of times per second. Although hydrogen bonds give water its remarkable strength, they are astonishingly short-lived. Each bond lasts only about a trillionth of a second before it snaps, and a new one forms with a different neighbor. In a single drop of water, this process happens countless times every moment, creating a flickering web of connections that is never quite the same from one instant to the next. If you could somehow slow time and watch the molecules at work, you would see a constant dance of attraction and release, partners switching in an endless, silent waltz. This rapid turnover is what allows water to flow so easily despite having such strong intermolecular forces. It can reshape itself around any container without losing its cohesive properties. The balance between strength and flexibility is what makes liquid water so uniquely suited to supporting life. It is firm enough to transport nutrients, yet fluid enough to move through the tiniest capillaries of a leaf. The angle between hydrogen atoms in water is about 104 degrees. If you could peer into a single water molecule, you would see its two hydrogen atoms spread apart at an angle of roughly 104.5 degrees. This is not quite the perfect angle you might expect from a balanced arrangement. The oxygen atom at the center holds two lone pairs of electrons that push the hydrogen atoms slightly closer together, squeezing the angle down from the ideal tetrahedral shape. This modest deviation has enormous consequences. The angle creates the polarity that makes water such an effective solvent and such a strong participant in hydrogen bonding. Even a few degrees of difference would alter the strength of those bonds and change the way water behaves at every scale. Scientists have studied this angle for over a century and continue to discover subtle effects that ripple outward from it. It is one of the smallest measurements in chemistry, yet it shapes the behavior of every ocean, river, and raindrop on Earth. Water molecules vibrate and rotate constantly, even in still liquid. A glass of water sitting untouched on a bedside table may look perfectly still, but at the molecular level, it is alive with motion. Every water molecule vibrates along its bonds, stretching and compressing millions of times each second. At the same time, the molecules spin and tumble in all directions, bouncing off their neighbors in an endless flurry of activity. These motions are driven by thermal energy, the heat stored within the liquid from its surroundings. Even at the freezing point, water molecules still vibrate, though they are locked into the rigid lattice of ice. The speed and intensity of these movements increase as the temperature rises, which is why hot water eventually reaches the point where molecules escape into the air as steam. This ceaseless molecular dance is completely invisible to the naked eye, yet it is responsible for everything from how quickly sugar dissolves in your tea to how rapidly heat spreads through a bath. Hydrogen atoms in water can tunnel through energy barriers at the quantum level. At the very smallest scales, water behaves in ways that seem to defy ordinary logic. Quantum tunneling allows the hydrogen atoms within a water molecule to pass through energy barriers that, according to classical physics, they should not be able to cross. Instead of climbing over the barrier, the atom essentially appears on the other side, as though it briefly ceased to exist in one place and materialized in another. This effect is a consequence of the wave-like nature of particles at the quantum level. In water, tunneling plays a subtle role in how hydrogen bonds form and break, slightly altering the rates of chemical reactions. Researchers have found evidence that tunneling is particularly important at low temperatures, where classical motion slows but quantum effects persist. It is a strange and beautiful idea that even in a quiet glass of water, the atoms are performing feats that blur the boundaries between what is possible and what is not. Water is the only substance found naturally in all three states on Earth. Most substances on our planet exist in just one state under normal conditions. Rocks are solid, the atmosphere is gaseous, but water moves effortlessly among all three. On any given day, you can find water as a solid in the ice caps, as a liquid in the oceans, and as a gas in the clouds above. No other natural substance on Earth shares this remarkable versatility at the temperatures and pressures found on our planet's surface. This triple presence is essential for the water cycle, which keeps fresh water circulating between the sea, the sky, and the land. It is also one of the reasons Earth is so hospitable to life. If water existed only as a liquid, there would be no rain. If it existed only as a gas, there would be no oceans. The ability to shift between states allows water to transport energy and matter across the globe in ways that no other molecule can match. At the triple point, water exists as solid liquid and gas simultaneously. There is a very precise combination of temperature and pressure at which water can exist in all three states at once. This is called the triple point, and it occurs at just above 0.01 degrees Celsius and a pressure of about 611 pascals, far lower than normal atmospheric pressure. At this delicate balance, ice, liquid water, and water vapor coexist side by side, each transforming freely into the others. It is a fragile equilibrium that is almost impossible to observe in everyday life, but in careful laboratory settings, you can watch ice gently sublimating into vapor while liquid water freezes and boils at the same time. The triple point is so precisely defined that it was once used as a fixed reference in the International Temperature Scale. It is a quiet reminder that in the right conditions, water does not have to choose between being solid, liquid, or gas. It can simply be all three at once. Ice expands when it freezes rather than contracting like most substances. Nearly every substance you can think of shrinks when it cools and solidifies. Metals contract, wax hardens into a denser form, but water does the opposite. When it freezes, it expands by roughly 9%, becoming less dense as a solid than as a liquid. This happens because the hydrogen bonds in ice lock the molecules into a rigid hexagonal lattice that spaces them further apart than they are in liquid water. The result is a crystal structure that is open and airy compared to the tumbling, close-packed arrangement of the liquid. This seemingly small quirk has enormous consequences for the planet. It means that ice floats, which insulates the water beneath and protects aquatic life during winter. If ice behaved like most other solids and sank, lakes and oceans could freeze from the bottom up, making it far more difficult for life to survive the cold seasons. Because ice floats, it insulates the water below and protects aquatic life. When winter descends on a lake, the surface water cools and eventually freezes into a sheet of ice. Because ice is less dense than liquid water, it stays on top rather than sinking to the bottom. This floating layer acts as an insulating blanket, slowing the loss of heat from the water beneath and keeping temperatures above freezing even when the air above is bitterly cold. Fish, amphibians, and countless microorganisms survive the winter in this sheltered liquid space below the ice. Without this peculiar property, the entire body of water could freeze solid, leaving nowhere for aquatic life to retreat. Over millions of years, this simple fact has shaped the evolution of freshwater ecosystems around the world. It is one of the quiet miracles of water chemistry, a small difference in density that preserves entire communities of living things through the harshest months. And it happens every winter, as reliably as the turning of the earth. If ice sank lakes and oceans, would freeze solid from the bottom up. Imagine a world where ice behaved like almost every other solid and sank when it formed. Each winter, the ice forming on the surface of a lake would drop to the bottom, exposing fresh liquid water to the cold air above. That new surface layer would freeze in turn and sink again, and this process would continue until the entire body of water had turned to solid ice from the bottom up. In the deepest parts of the ocean, sunlight would never reach to thaw the accumulated ice, and over time vast regions of the sea floor would be permanently frozen. Aquatic life would have almost nowhere to shelter during cold seasons, and the ecosystems we know today could never have developed. The fact that ice floats is one of the most consequential quirks in all of chemistry. It is a small twist of molecular geometry that has kept the oceans liquid and life-sustaining for billions of years. Water reaches its maximum density at about 4 degrees Celsius. As most liquids cool, they become steadily denser until they solidify. Water follows this pattern only to a point. It reaches its greatest density at about 4 degrees Celsius, and below that temperature, it actually begins to expand again as it approaches freezing. This peculiar behavior is caused by the hydrogen bonds between water molecules beginning to arrange themselves into the open lattice structure of ice before the water has fully frozen. The practical effect is profound. In a cooling lake, the densest water at 4 degrees sinks to the bottom, while the slightly lighter, colder water remains near the surface where it eventually freezes. This means the deepest parts of a lake tend to stay at a relatively stable temperature even in the harshest winters. Fish and other organisms take refuge in these deeper layers, surviving the cold in a pocket of liquid that remains just above freezing. It is a subtle detail that quietly safeguards life beneath the ice. Water can be supercooled below freezing without turning to ice. Under the right conditions, water can remain liquid even when its temperature drops well below the normal freezing point. This phenomenon is called supercooling, and it happens when the water is very pure and very still, with no particles or rough surfaces to act as starting points for ice crystals. In laboratory settings, researchers have cooled water to nearly -40 degrees Celsius without it freezing. The molecules are ready to crystallize, but lack the initial nudge to begin. The slightest disturbance, a tap on the container, a speck of dust, or even a tiny vibration, can trigger an almost instant transformation from liquid to solid. In nature, supercooled water exists in high-altitude clouds, where tiny droplets remain liquid far below freezing until they encounter ice crystals or dust particles. It is a fragile and fleeting state, a quiet pause before the inevitable shift from water to ice. Hot water can sometimes freeze faster than cold water in the Mpemba effect. It seems to contradict common sense, but under certain conditions, hot water can freeze more quickly than cold water. This counterintuitive phenomenon is known as the Mpemba effect, named after a Tanzanian student who noticed it while making ice cream in the 1960s. Despite decades of research, no single explanation has been universally accepted. Some scientists suggest that hot water evaporates faster, reducing its volume and therefore needing less cooling. Others point to differences in the way dissolved gases escape, or the way convection currents distribute heat within the container. There may even be subtle effects at the molecular level, where the arrangement of hydrogen bonds differs between hot and cold water. What makes the Mpemba effect so fascinating is that such a simple question about something as familiar as water can still resist a definitive answer. It is a gentle reminder that even the most ordinary substances can harbor mysteries that science has yet to fully resolve. Under extreme pressure, water forms exotic states like supersonic ice. Deep inside giant planets, conditions are so extreme that water behaves in ways never seen on Earth's surface. At pressures millions of times greater than our atmosphere and temperatures of thousands of degrees, water can enter a state called supersonic ice. In this strange phase, the oxygen atoms lock into a solid crystal lattice, while the hydrogen atoms flow freely through it like a liquid carrying electrical charge as they move. The result is a material that is simultaneously solid and conducting, unlike any form of water we encounter in daily life. Scientists first predicted supersonic ice through computer simulations and have since confirmed its existence using powerful lasers in laboratory experiments. This exotic state is thought to exist deep within the interiors of Uranus and Neptune, where it may contribute to the unusual magnetic fields of those distant ice giants. It is a remarkable example of how pressure can transform even the most familiar substance into something entirely alien. Inside, ice giants like Neptune water may cause diamond rain. The interiors of Uranus and Neptune are believed to harbor conditions so extreme that carbon atoms are squeezed out of simple molecules like methane and compressed into solid diamonds. These diamonds, formed thousands of kilometers beneath the planet's cloud tops, may then sink slowly through layers of dense, hot fluid toward the core, falling like rain through an alien ocean. The water present at these depths exists in exotic high-pressure forms that bear little resemblance to anything on Earth. Scientists have recreated similar conditions in the laboratory using intense laser pulses to compress materials to planetary pressures, and the results support the idea that diamond formation is plausible. If diamond rain truly occurs, it would represent one of the most extraordinary processes in the solar system. a place where two of the most familiar substances, water and carbon, combine under unimaginable forces. It is a dreamlike image, diamonds drifting through hot, pressurized water in the deep interior of a distant world. Every snowflake begins as ice forming around a tiny particle of dust. A snowflake does not form from nothing. High in the atmosphere, a microscopic particle of dust, pollen, or volcanic ash drifts through a cloud of supercooled water droplets. When a droplet encounters one of these tiny particles, it finally has a surface upon which to crystallize, and a snowflake is born. The initial ice crystal is barely visible, a speck smaller than the width of a human hair. But as it tumbles through the cloud, more water vapor freezes onto its surface, building up the intricate branches and plates that make snowflakes so beautiful. The process can take anywhere from a few minutes to over an hour, depending on conditions within the cloud. Each snowflake's journey through varying temperatures and humidity levels shapes its final pattern, ensuring that no two follow exactly the same path. It all begins with a single grain of dust, a quiet seed around which the crystal slowly grows. Snowflakes always form with six-sided symmetry due to molecular geometry. The hexagonal symmetry of snowflakes is not a matter of chance. It arises directly from the way water molecules bond to one another as they freeze. When water crystallizes, the molecules arrange themselves into a lattice built upon hexagonal rings, each ring made of 6 water molecules linked by hydrogen bonds. This underlying six-fold pattern dictates the overall shape of the growing crystal, which is why snowflakes develop 6 main branches or 6 flat sides. The symmetry is maintained as the crystal grows because all 6 directions experience the same conditions of temperature and humidity at the same time. Different environmental conditions produce different styles of hexagonal crystal, from simple flat plates to elaborate branching stars, but the 6-sided theme remains constant. Scientists have been studying snowflake geometry for centuries, beginning with the early observations of the astronomer Johannes Kepler. It remains one of nature's most elegant demonstrations of how molecular structure scales up into visible beauty. No two snowflakes are exactly alike because each follows a unique path through the clouds. The idea that every snowflake is unique is more than a poetic saying. As a snowflake forms, it tumbles through a cloud where temperature, humidity, and air currents change from one moment to the next. Each tiny shift in conditions alters the way new ice crystals deposit on the growing flake, producing a slightly different pattern of branches and plates. Because no two snowflakes follow precisely the same path through these ever-changing conditions, no two accumulate ice in exactly the same way. The number of possible arrangements is staggeringly large, far greater than the total number of snowflakes that have ever fallen on Earth. Even snowflakes that form side by side will quickly diverge in shape as they drift apart and encounter different pockets of air. It is a humbling thought that something as common as a snowfall is composed entirely of individuals, each one a tiny, unrepeatable work of frozen geometry drifting gently down from the sky. A single snowflake may contain around 10 quintillion water molecules. Despite its delicate appearance, a single snowflake is made up of an almost incomprehensible number of water molecules. A typical snowflake weighs roughly 3/millionths of a gram, yet that tiny mass translates to approximately 10 quintillion individual molecules, a number so vast that writing it out in full would take 19 digits. Every one of those molecules is locked into the hexagonal lattice of ice, connected to its neighbors by hydrogen bonds. The sheer quantity explains how such intricate patterns can form. With so many building blocks available, even the subtlest changes in temperature or humidity can redirect the growth of branches in slightly different directions. It also means that the information contained in the shape of a single snowflake is extraordinarily complex. a frozen record of every tiny atmospheric change the crystal encountered on its journey from cloud to ground. And yet, for all its hidden complexity, a snowflake melts in a moment, releasing those molecules back into the quiet flow of water. Fresh snow is mostly trapped air, which makes it white and insulating. When snow first falls, it is remarkably light and fluffy because the intricate shapes of the snowflakes trap large pockets of air between them. A fresh blanket of snow can be more than 90% air by volume, which is why it crunches softly underfoot and why a deep snowfall can weigh surprisingly little. That trapped air is also what gives snow its brilliant white appearance. Light entering the snow is scattered in all directions by the countless tiny surfaces of the ice crystals, and because all wavelengths of visible light are reflected equally, the snow appears white. The same trapped air makes snow an excellent insulator. Beneath a thick layer of snow, the ground stays warmer than the frigid air above, and small animals like voles and mice create tunnels in this sheltered zone to survive the winter. Farmers have long known that a good snow cover protects crops from frost damage. It is a gentle paradox that something born of cold can offer so much warmth. Glaciers form when layers of snow compress over centuries into dense blue ice. A glacier begins as nothing more than snowfall that does not melt. Year after year, fresh snow accumulates on top of older layers, and under the increasing weight, the lower layers are gradually compressed. Air is squeezed out, and the once fluffy crystals merge into dense, interlocking grains of ice. Over decades and centuries, this process transforms the snow into glacial ice, a material so dense and compact that it absorbs most wavelengths of light except blue, giving glaciers their characteristic deep blue or turquoise hue. Some of the ice at the base of the largest glaciers has been under pressure for hundreds of thousands of years. Glaciers hold about 69% of the world's fresh water, locked in vast sheets and slow-moving rivers of ice. They shape the landscape beneath them, carving valleys and depositing rubble as they creep forward. When they eventually melt, they release water that has been held in frozen storage since long before recorded history began. Some water molecules have remained frozen in polar ice for thousands of years. Deep within the ice sheets of Antarctica and Greenland, there are layers of ice that formed from snowfall thousands upon thousands of years ago. These ancient layers have been gradually buried under subsequent snowfalls, compressed and sealed away from the atmosphere above. Some of the deepest ice cores drilled from Antarctica contain water that last fell as snow more than 800,000 years ago. Tiny bubbles of ancient atmosphere are trapped alongside the frozen water, preserving a record of what the air was like when dinosaurs were long gone, but humans had not yet appeared. Scientists extract these cores and analyze the bubbles to understand past climates, tracing the rise and fall of temperatures and greenhouse gases across the ages. The water molecules themselves have remained locked in place, unchanged, while entire civilizations rose and fell above them. It is moving to think that a molecule frozen in polar ice tonight may not flow as liquid water again for millennia to come. When glacial ice melts, it releases water that has not flowed since the last ice age. As glaciers retreat in a warming climate, they release water that has been frozen since the last great ice age, roughly 10 to 20,000 years ago. This meltwater carries with it a chemical and isotopic signature that is distinctly different from modern rainfall, allowing scientists to identify it in rivers and lakes downstream. In some cases, the melting reveals landscapes that have not seen the light of day for millennia, complete with preserved plants and insects. The released water joins modern rivers and eventually reaches the sea, where it mixes with contemporary ocean water. For the molecules themselves, it is a sudden return to the liquid world after an extraordinarily long rest. They resume their role in the water cycle as though nothing has changed, flowing downhill, evaporating, and falling again as rain. There is something quietly poetic about water that froze in an age of mammoths, now trickling through a modern valley in the warmth of a summer afternoon. Water has unusually high surface tension compared to most liquids. If you watch a drop of water on a leaf, you will notice it clings together in a rounded bead rather than spreading flat. This is because water has an exceptionally high surface tension, the result of the strong hydrogen bonds between its molecules. At the surface of a body of water, molecules are pulled inward by their neighbors below and beside them, but there are no water molecules above to balance the pull. This creates a thin, elastic-like film on the surface that resists being broken. Water's surface tension is higher than that of almost any other common liquid, exceeded only by mercury among everyday substances. This invisible film is strong enough to support the weight of small insects and even thin metal objects like a carefully placed needle. Surface tension also shapes the way raindrops form, how bubbles hold their shape, and how water moves through the pores of soil. It is a subtle force with far-reaching effects across nature. Surface tension allows some insects to walk on water without sinking. Water striders are among the most elegant examples of surface tension in action. These slender insects glide across the surface of ponds and streams as though skating on glass, their long legs distributing their weight so evenly that the surface film of the water never breaks. Tiny hairs on their legs trap air and increase the contact area, further reducing the pressure on any single point. The dimples they create on the water's surface are visible to the eye, small depressions where the elastic film bends but does not rupture. Other creatures, too, take advantage of this invisible barrier. Some spiders sprint across puddles, and certain beetles use surface tension to propel themselves forward by releasing compounds that locally weaken the surface behind them. For these small animals, the surface of a pond is not a boundary but a highway, a solid platform made entirely of the gentle pull between water molecules. It is a quiet demonstration of how molecular forces scale up into the visible world. Some spiders trap air bubbles underwater to breathe, like a diving bell. The water spider, found in parts of Europe and Asia, spends nearly its entire life beneath the surface of freshwater ponds. It achieves this remarkable feat by trapping a bubble of air in the fine hairs that cover its abdomen and carrying it underwater like a tiny silver backpack. The spider then weaves a dome of silk among submerged plants and fills it with air brought down from the surface, creating a miniature diving bell. Inside this bubble, the spider rests, feeds, and even raises its young. The air supply is not entirely sealed off from the surrounding water. Oxygen dissolved in the pond water diffuses into the bubble, while carbon dioxide diffuses out, allowing the spider to refresh its air supply without surfacing as frequently. This elegant use of physics and biology means the spider can remain submerged for hours or even a full day at a time. It is a beautiful example of how life finds inventive ways to exploit the properties of water. Water drops form spheres because surface tension pulls the surface inward. When a drop of water falls freely through the air, it naturally draws itself into a sphere. This happens because surface tension acts equally in all directions, pulling every part of the drop's surface inward toward its center. A sphere is the shape that encloses the greatest volume with the smallest surface area, so it is the most energy-efficient form the drop can take. In practice, falling raindrops are not perfect spheres because air resistance flattens them slightly on the bottom, giving larger drops a shape more like a hamburger bun. But very small droplets, such as those in fog or mist, are nearly perfect spheres. In the weightlessness of space, where air resistance is absent, water forms exquisitely round globes that drift and wobble in a mesmerizing way. The tendency to form spheres is one of the most visually striking consequences of surface tension, a reminder that water is always seeking the calmest, most balanced state it can find. In zero gravity, water forms perfect floating spheres. Aboard the International Space Station, astronauts regularly demonstrate one of the most beautiful consequences of surface tension. When a blob of water is gently released in microgravity, it draws itself into an almost perfect sphere and floats freely in the cabin air. Without the downward pull of gravity to flatten it or press it against a surface, the water is shaped entirely by the inward pull of its own surface tension. These floating globes wobble and quiver at the slightest breath, reflecting light from all angles like miniature crystal balls. If a small air bubble is trapped inside, it migrates to the center and sits there motionless, creating a sphere within a sphere. Astronauts have injected dyes and effervescent tablets into these floating spheres on camera, producing mesmerizing displays of swirling color. These demonstrations are more than just entertainment. They provide scientists with valuable insights into how fluids behave when freed from gravity, knowledge that is useful for designing life support systems and managing fuel in spacecraft. Capillary action allows water to climb upward through narrow spaces. Water has the remarkable ability to defy gravity, but only on a small scale. In narrow tubes, thin cracks, and the tiny spaces between fibers, water creeps steadily upward without any pump or pressure to push it. This process is called capillary action, and it results from the combined effects of adhesion and cohesion. Water molecules are attracted to the walls of the tube they are in, a property called adhesion, and they are also attracted to one another through cohesion and hydrogen bonding. Together, these forces pull the water up along the walls, and the rest of the liquid follows. The narrower the tube, the higher the water can climb. Capillary action is what draws water into a sponge, wicks moisture through a paper towel, and helps move water through the pores of soil to reach plant roots. It is a quiet, persistent force that works against gravity every moment of every day, sustaining life in countless ways you rarely notice. Trees use capillary action to lift water over 100 meters to their highest leaves. The tallest trees on Earth, such as the coastal redwoods of California, can reach heights exceeding 100 meters. Getting water from the roots to the uppermost leaves presents an extraordinary engineering challenge, one that nature solves with elegant simplicity. The main mechanism involves transpiration, the evaporation of water from tiny pores on the leaf surface. As each molecule of water escapes into the air, it pulls the next molecule behind it, creating a continuous chain of water stretching from the leaves all the way down to the roots. This chain is held together by the cohesive strength of hydrogen bonds and is drawn upward through narrow vessels in the trunk by the same capillary forces that pull water through a thin tube. The system works without any pump or moving parts, powered entirely by the energy of sunlight driving evaporation at the top. It is one of the most impressive feats of water transport in the natural world, a silent column of liquid climbing skyward against the pull of the earth. Water is often called the universal solvent because it dissolves so many substances. Water dissolves more substances than any other common liquid, which is why chemists have long called it the universal solvent. Its polar nature is the key. The slightly positive hydrogen ends and the slightly negative oxygen end of each molecule are attracted to charged particles and polar molecules in other substances. When you drop a pinch of salt into water, the water molecules surround each sodium and chloride ion, pulling them apart and holding them in solution. The same process works on sugars, gases, minerals, and countless other compounds. This dissolving power is essential for life. Nutrients must dissolve in water before plants can absorb them through their roots. Oxygen must dissolve in blood plasma before it can reach your cells. Rivers dissolve minerals from rock and carry them to the sea, slowly shaping the chemistry of the ocean over millions of years. Of course, water cannot dissolve everything. Oils and fats resist it, which is why they float on the surface rather than mixing in. Pure water is a poor conductor of electricity until minerals dissolve in it. You may have heard that water and electricity are a dangerous combination, and that is true of the water we encounter in daily life. But perfectly pure water is actually a remarkably poor conductor of electricity. This is because pure water contains very few free ions, the charged particles that carry electrical current through a liquid. In practice, however, the water around us is never truly pure. Rainwater picks up dissolved carbon dioxide from the air, forming a weak acid. Tap water contains minerals like calcium and sodium from the pipes and treatment process. Seawater is rich in dissolved salts. Each of these dissolved substances releases ions into the water, transforming it into an effective conductor. This is why standing in a puddle during a lightning storm is so dangerous. The dissolved minerals in the water provide a clear path for the electrical current. The difference between pure and impure water is a subtle but critical distinction that underpins both safety advice and countless industrial processes. Over millions of years, water dissolves solid rock into caves and canyons. Water is patient and persistent, and given enough time, it can carve through the hardest stone. Rainwater absorbs carbon dioxide from the atmosphere and the soil, forming a mild carbonic acid that slowly dissolves limestone and other soluble rocks. Drop by drop, over hundreds of thousands of years, this gentle acid eats away at the rock from within, hollowing out vast underground chambers and passageways. The result is the spectacular cave systems found on every continent, decorated with stalactites hanging from the ceiling and stalagmites rising from the floor. On the surface, the same process carves river gorges and canyons of breathtaking scale. The Grand Canyon, for example, was shaped over millions of years by the steady flow of the Colorado River cutting through layer after layer of ancient rock. Water does not need to be powerful to reshape the world. It simply needs time, and time is something water has had in abundance since the very first rains fell on the young earth. Every grain of salt in the ocean began as rock dissolved by rainwater. The ocean's saltiness did not come from the sea itself. It was delivered, grain by grain, by rivers flowing over rock. When rain falls on land, it seeps through soil and percolates through stone, dissolving tiny amounts of minerals along the way. These dissolved minerals, including sodium and chloride, are carried by streams and rivers until they eventually reach the sea. Once in the ocean, the water evaporates and rises into the atmosphere, but the dissolved salts are left behind, gradually accumulating over billions of years. This slow, relentless process has made the ocean about 3.5% salt by mass, enough to give seawater its distinctive taste and to make it denser than fresh water. The minerals in the ocean also include calcium, magnesium, and potassium, each delivered by the same patient mechanism. Every grain of sea salt you have ever tasted began its journey as part of a solid rock somewhere on land, dissolved by the quiet persistence of water. The ocean grows slightly saltier over geological time as rivers deliver more minerals. The process of rivers carrying dissolved minerals to the sea has been going on for billions of years, and it has not stopped. Every day, rivers around the world deliver fresh loads of dissolved salts to the ocean. Over long stretches of geological time, this steady input has gradually increased the ocean's salinity. However, the rate of increase is not constant because various processes also remove salt from the water. Minerals precipitate out on the sea floor, sea spray carries small amounts of salt onto land, and hydrothermal vents on the ocean floor exchange ions with the rock beneath. These competing processes have kept the ocean's salt levels relatively stable over the past several hundred million years, though small fluctuations continue. The balance between salt delivered by rivers and salt removed by geological processes is one of those quiet equilibria that keep the planet's chemistry in check. It is a slow and gentle tug of war, played out across eons, that determines the flavor of the sea. Under extreme deep-sea pressure, water becomes an even more powerful solvent. At the bottom of the ocean, the weight of kilometers of water above creates pressures that are hundreds or even 1,000 times greater than at the surface. Under these conditions, water's dissolving power is enhanced. The increased pressure forces water molecules closer together, intensifying their interactions with dissolved substances and allowing them to break apart minerals that would resist dissolution at the surface. Near hydrothermal vents on the ocean floor, superheated water under immense pressure dissolves metals and minerals from the surrounding rock, creating plumes of dark, mineral-rich fluid known as black smokers. These plumes carry dissolved iron, manganese, zinc, and other elements into the surrounding water, building up chimney-like structures of deposited minerals. The extreme conditions at the deep-sea floor create a chemical environment unlike anything on the surface, where water acts as a far more aggressive solvent. It is a reminder that the properties of water are not fixed, but shift dramatically depending on the temperature and pressure it encounters. Water carries nutrients through soil to plant roots and through blood to every cell. Water is the great transporter of the living world. In the soil, it dissolves mineral nutrients and carries them in solution to plant roots, where they are absorbed and distributed throughout the plant. Without water, these nutrients would remain locked in the soil, inaccessible and useless. Inside the bodies of animals, water performs the same role in a different setting. Blood, which is mostly water, carries dissolved oxygen from the lungs to every cell and returns carbon dioxide to be exhaled. It transports glucose from the digestive system, hormones from glands, and waste products to the kidneys for removal. The lymphatic system, too, relies on water to move immune cells and fluid throughout the body. In every ecosystem on Earth, water serves as the universal delivery system, connecting the chemistry of the soil to the chemistry of life. Without this simple liquid acting as a carrier, the elaborate network of biological processes that sustains all living things would grind to a halt. The human body is approximately 60 to 70% water by weight. You are, in the most literal sense, mostly water. The average adult human body is roughly 60 to 70% water by mass, with the exact proportion depending on age, sex, and body composition. Newborn babies have the highest percentage, sometimes exceeding 75%, while the proportion decreases gradually with age. Water is found in every part of you. It fills your cells, cushions your organs, lubricates your joints, and regulates your temperature. It makes up most of the volume of your blood and the fluid that bathes your brain and spinal cord. Even your bones, which seem so solid and dry, contain a significant fraction of water. Losing just a small percentage of your body water can impair concentration and physical performance, and losing more than about 15% can be life-threatening. The water inside you is not static. It cycles through constantly, entering as food and drink and leaving as breath, sweat, and waste. You are a quietly flowing river of water in human form. Your brain is about 75% water. Of all the organs in your body, the brain is one of the most water-rich. Roughly 3/4 of its mass is water, which plays a critical role in every function the brain performs. Water acts as a cushion, surrounding the brain in a layer of cerebrospinal fluid that absorbs shocks and protects the delicate neural tissue from the hard interior of the skull. It is also essential for the chemical reactions that produce neurotransmitters, the signaling molecules that allow your brain cells to communicate with one another. Even mild dehydration can affect how clearly you think, reducing attention, slowing reaction times, and making it harder to form new memories. The brain has no way to store water on its own, so it depends on a constant supply delivered through the bloodstream. When you feel a headache coming on after a long day without drinking enough, it is often your brain signaling that its water supply is running low. A simple glass of water can be one of the kindest things you do for your mind. Blood is more than 90% water. The red liquid pumping through your veins is, by volume, overwhelmingly water. Blood plasma, the straw-colored fluid in which red and white blood cells are suspended, is composed of more than 90% water. This watery base is what allows plasma to flow smoothly through the narrowest capillaries and to carry dissolved substances to every corner of the body. Oxygen binds to hemoglobin inside red blood cells, but it must first dissolve in the watery plasma before it can be transferred. Nutrients from your last meal travel in this same liquid, as do hormones, antibodies, and waste products heading for the kidneys. The high water content of blood also plays a role in regulating body temperature. When you are too warm, blood vessels near the skin dilate, allowing more of this warm, water-rich fluid to release heat to the air. When you consider that an adult human carries roughly 5 liters of blood, you begin to appreciate just how much water is quietly circulating through you at every moment. Every cell in your body maintains precise water pressure across its membrane. Each of the trillions of cells in your body is a tiny water-filled compartment enclosed by a membrane that carefully regulates what passes in and out. The balance of water pressure across this membrane is critical. If too much water enters, the cell swells and may burst. If too much leaves, the cell shrivels and cannot function. This equilibrium is maintained through osmosis, the movement of water from areas of lower solute concentration to areas of higher concentration through the semi-permeable membrane. Your cells actively manage this pressure by pumping ions in and out, adjusting the concentration on each side of the membrane with remarkable precision. In plants, this water pressure, known as turgor pressure, is what keeps stems upright and leaves firm. When a plant wilts, it is because its cells have lost water pressure. In both plants and animals, the careful management of water across cell membranes is one of the most fundamental processes of life, a quiet balancing act that never pauses. Water molecules surround and stabilize the double helix of DNA. The famous double helix of DNA does not exist in a vacuum. It is bathed in a sheath of water molecules that play an active role in maintaining its structure. Water molecules form hydrogen bonds with the nucleotide bases and the sugar phosphate backbone of the DNA strand, helping to hold the two strands together in their characteristic twisted ladder shape. Without this surrounding layer of water, the helix would lose its stability and the hydrogen bonds between the base pairs would weaken. Researchers have found that the precise arrangement of water molecules around DNA affects how the helix bends, twists, and interacts with the proteins that read and copy genetic information. In a very real sense, water is not just the medium in which DNA exists, but an active participant in its function. The blueprint for every living thing on Earth depends on a delicate partnership with the most common liquid on the planet. It is another quiet reminder that life and water are inseparable at the most fundamental level. Proteins fold into their functional shapes, partly because of water interactions. A protein is made from a long chain of amino acids, but that chain is useless until it folds into the correct three-dimensional shape. Water plays a central role in guiding this folding process. Many amino acids have side chains that either attract or repel water. The hydrophobic or water-fearing side chains tend to cluster together in the interior of the protein, away from the surrounding water. Meanwhile, the hydrophilic or water-loving side chains face outward, interacting comfortably with the watery environment. This sorting process is one of the main driving forces behind protein folding. Without water, these forces would not exist, and proteins would remain floppy, functionless threads. Once folded, proteins carry out nearly all the work inside a cell, from catalyzing chemical reactions to transporting molecules and sending signals. The fact that water shapes the architecture of these molecular machines means that virtually every biological process in your body owes something to the interaction between amino acids and the liquid that surrounds them. Tears contain water mixed with proteins, oils, and mucus. Tears are far more complex than simple salty water. Each tear is a layered fluid made of three main components. The outermost layer is a thin film of oil produced by tiny glands along the edges of the eyelids, which slows evaporation and keeps the tear surface smooth. Beneath that is the watery middle layer, which makes up the bulk of the tear and contains dissolved salts, proteins, and antibacterial enzymes. Closest to the eye is a layer of mucus that helps the tear adhere evenly to the curved surface of the cornea. Together, these three layers protect, nourish, and lubricate the eye with every blink. Emotional tears have a slightly different composition from those produced to wash away irritants. They contain higher levels of certain stress hormones and natural painkillers, which some researchers believe may play a role in emotional relief. Whether you cry from sadness, joy, or a gust of wind, your tears are a carefully formulated solution designed to care for one of your most delicate organs. Sweating cools your body as water evaporates from your skin. When your body temperature begins to rise, whether from exercise, warm weather, or a fever, your sweat glands spring into action. They release a thin layer of water mixed with small amounts of salt and other substances onto the surface of your skin. As this water evaporates into the air, it carries heat away from your body, cooling you down in the process. This mechanism is called evaporative cooling, and it is one of the most effective temperature regulation strategies in the animal kingdom. Humans are among the best sweaters on the planet, capable of producing several liters of sweat per hour during intense physical activity. This ability is thought to have given our ancestors an advantage in long distance, running under the hot African sun. Other animals rely on panting or finding shade, but we can simply sweat our way through the heat. Of course, sweating only works efficiently when the surrounding air is dry enough to allow evaporation, which is why humid days feel so oppressively warm. Your body produces about half a liter to a liter of saliva each day. Every day, the glands in your mouth quietly produce between half a liter and a full liter of saliva, a watery fluid that performs many more tasks than you might expect. Saliva begins the process of digestion before food even reaches your stomach, with enzymes starting to break down starches the moment you begin chewing. It also lubricates your mouth, making it easier to speak and swallow, and washes away food particles and bacteria that might otherwise cause tooth decay. Saliva contains antibacterial compounds that help protect the lining of your mouth from infection. It even plays a role in taste, since flavor molecules must dissolve in the liquid coating of your tongue before your taste buds can detect them. Without enough saliva, eating would become painful, speaking would be difficult, and the risk of dental problems would rise dramatically. This unassuming fluid is produced steadily throughout the day and night, though at a slower rate while you sleep. It is one of the many ways water works silently within you. The water you drink today will return to the environment within days or weeks. Water does not stay in your body for very long. Most of the water you drink passes through you within a matter of days. It enters through your mouth, is absorbed in the intestines, circulates through your blood, carries nutrients and waste to the appropriate places, and then exits through urine, sweat, breath, and other bodily processes. The average residence time of a water molecule in the human body is roughly 1 to 2 weeks, depending on your level of activity and the surrounding temperature. This means you are constantly exchanging water with the outside world, taking in fresh supplies and releasing used ones back into the environment. The water that leaves your body re-enters the water cycle, evaporating into the atmosphere, falling as rain, seeping into the ground, or flowing into rivers and oceans. You are, in a very real sense, a temporary stop on a journey that the water has been making for billions of years. It flows through you and carries on. A single cloud can contain millions of kilograms of water. Clouds may look light and fluffy, drifting effortlessly across the sky, but they are far heavier than they appear. A typical cumulus cloud, the kind you might see on a warm summer afternoon, can contain several 100,000 kilograms of water in the form of tiny suspended droplets. Larger storm clouds can hold millions of kilograms. The reason clouds float despite this enormous weight is that the water is distributed across a vast volume of air, and each individual droplet is so small and light that it is kept aloft by rising air currents. A single cloud droplet is only about 10 to 20 micrometers across, far smaller than the diameter of a human hair. Billions of these tiny droplets come together to form the visible mass of a cloud. When conditions change and the droplets grow large enough, they begin to fall as rain, releasing a fraction of the cloud's stored water back to the surface. It is a gentle reminder that the sky carries far more water than our eyes suggest. Water vapor is the most powerful greenhouse gas in Earth's atmosphere. When people think of greenhouse gases, carbon dioxide and methane usually come to mind first. But the most abundant and powerful greenhouse gas in Earth's atmosphere is actually water vapor. It absorbs and re-emits infrared radiation more effectively than any other naturally occurring gas, trapping heat near the surface and keeping the planet warm enough to support life. Without water vapor, the average surface temperature of the Earth would drop well below freezing. However, water vapor's role in the climate is complicated by feedback loops. As the atmosphere warms, it can hold more water vapor, which in turn traps more heat, amplifying the warming effect. At the same time, increased water vapor can lead to more cloud formation, and clouds can either warm or cool the surface depending on their type and altitude. Scientists study these interactions carefully to understand how the climate will change in the coming decades. Water vapor is both the planet's natural thermostat and one of the most complex variables in climate science. Clouds form around microscopic particles called condensation nuclei. A cloud cannot form from thin air alone. Water vapor needs a surface upon which to condense, and in the atmosphere, those surfaces are provided by tiny airborne particles called condensation nuclei. These particles can be almost anything: grains of dust, sea salt crystals, pollen, volcanic ash, or even soot from fires. Each one is impossibly small, often less than a micrometer across, yet it is enough to give water vapor a foothold. When moist air rises and cools, the vapor molecules begin to gather around these nuclei, forming the microscopic droplets that make up a cloud. Without condensation nuclei, the air would need to become far more supersaturated before clouds could form, and the sky would look very different. In clean ocean air, there are fewer nuclei, so cloud droplets tend to be larger and fewer in number. In polluted air, the abundance of particles produces many tiny droplets, which can change how the cloud reflects sunlight and how readily it produces rain. Rain forms when cloud droplets merge and grow heavy enough to fall. Inside a cloud, vast numbers of tiny water droplets float suspended in the air, each one far too small to fall as rain. For precipitation to occur, These droplets must grow much larger, and they do so by colliding and merging with one another in a process called coalescence. As air currents swirl within the cloud, droplets of slightly different sizes drift at different speeds, increasing the chance of collision. Each merger produces a slightly larger droplet, which falls a little faster and sweeps up even more of its neighbors. In colder clouds, a different process dominates. Ice crystals grow at the expense of surrounding supercooled water droplets, since ice has a lower vapor pressure than liquid water. These crystals eventually become heavy enough to fall, melting into raindrops if they pass through warmer air on the way down. A single raindrop that lands on your window may have consumed 1 million smaller cloud droplets during its formation. The journey from mist to raindrop is a quiet cascade of tiny collisions. The smell of rain, called petrichor, comes from oils and bacterial compounds in soil. There is a distinctive, earthy fragrance that fills the air just after rain falls on dry ground, and it has a name, petrichor. The word was coined in the 1960s from the Greek words for stone and the ethereal fluid of the gods. The scent comes from a combination of sources. Plants release oils during dry periods that accumulate in the soil and on rocks. When rain arrives, the impact of the drops disturbs the surface and launches these oils into the air as tiny aerosols. At the same time, a compound called geosmin, produced by soil-dwelling bacteria, is released when the moisture reactivates the microbes. Together, these substances create the unmistakable smell that so many people find calming and pleasant. The human nose is remarkably sensitive to geosmin, able to detect it at concentrations as low as a few parts per trillion. Petrichor is one of nature's most beloved scents, a quiet gift that arrives with the first drops of rain after a long dry spell. Lightning occurs when ice and water collide violently inside storm clouds. A bolt of lightning is one of the most dramatic displays of energy in nature, and it begins with water and ice inside a towering storm cloud. As the cloud's powerful updrafts carry water droplets upward, they freeze into ice crystals at higher altitudes. These ice crystals collide with heavier particles of slush and hail that are falling downward, and with each collision, a tiny transfer of electrical charge occurs. Over time, a massive charge separation builds up within the cloud, with positive charges accumulating near the top and negative charges concentrating near the base. When the electrical difference becomes too great, the air between the cloud and the ground, or between different parts of the cloud, breaks down in a sudden discharge of energy. The lightning bolt heats the air around it to temperatures hotter than the surface of the sun, causing the air to expand explosively and produce the crack of thunder. All of this begins with the simple collision of water in its different states, quietly building toward a spectacular release. About 97% of all water on Earth is saltwater in the oceans. If you could gather all the water on Earth into a single container, the vast majority of it would be salty. Roughly 97% of the planet's water is found in the oceans, seas, and saltwater bodies, leaving only about 3% as freshwater. That tiny fraction must supply every river, lake, aquifer, glacier, and raindrop on the planet. The sheer dominance of saltwater is a consequence of billions of years of rivers carrying dissolved minerals to the sea, where the water evaporates but the salts remain. The oceans are by far the largest reservoir of water on Earth, and they play a central role in regulating the climate, absorbing heat from the sun and redistributing it around the globe through currents. For humans and most land-dwelling organisms, the ocean's water is not directly usable without desalination, a process that remains energy-intensive and expensive. It is a sobering thought that we live on a planet covered in water, yet the portion we can readily drink is vanishingly small. Most freshwater is locked in glaciers and ice caps. Of the roughly 3% of Earth's water that is fresh, the largest share is not flowing in rivers or filling lakes. It is frozen. Glaciers and the polar ice caps of Antarctica and Greenland hold about 69% of all the freshwater on the planet. These vast stores of ice represent water that fell as snow over thousands or even millions of years and was gradually compressed into dense glacial ice. If all of this ice were to melt, global sea levels would rise dramatically by an estimated 60 to 70 meters. The remainder of the world's freshwater is found underground in aquifers, with only a tiny sliver present in surface rivers and lakes. This means that the water you see flowing in streams and filling reservoirs represents a remarkably small fraction of the total. Most of the planet's freshwater is locked away in frozen vaults at the poles and in high mountain ranges, slowly releasing meltwater that feeds rivers and sustains communities far downstream. Less than 1% of Earth's water is readily accessible freshwater. When you combine all the water in rivers, lakes, reservoirs, and the shallow portions of underground aquifers that are easy to reach, the total amounts to less than 1% of all the water on Earth. This slender fraction must supply the drinking water, agriculture, and industry of over 8 billion people, as well as sustain every freshwater ecosystem on the planet. The rest is either locked in ice, dissolved in salt water, or buried too deep underground to be practically extracted. This scarcity is not evenly distributed across the globe. Some regions enjoy abundant rainfall and plentiful rivers, while others face chronic water shortages that affect millions of lives. Climate change, population growth, and pollution are adding further pressure to these limited supplies. It is a quiet but pressing reality that the water readily available for human use is a tiny sliver of a vast planetary total. Protecting and managing this precious resource is one of the most important challenges of our time. Deep aquifers hold ancient water that fell as rain thousands of years ago. Beneath the surface of the Earth, vast reservoirs of water lie hidden in porous rock formations called aquifers. Some of these underground stores contain water that seeped down from the surface thousands or even tens of thousands of years ago. Known as fossil water, this ancient groundwater has been sitting in the darkness, insulated from the atmosphere above, for longer than recorded human history. In parts of North Africa and the Arabian Peninsula, entire communities depend on fossil water that fell as rain during the last ice age, when the climate was wetter and rivers flowed across what is now desert. Because these aquifers are being depleted far faster than they can be naturally recharged, the water they contain is effectively a non-renewable resource. Once pumped to the surface and used, it enters the modern water cycle and may never return to the depths from which it came. Drawing from these reserves is like spending savings that took millennia to accumulate, a reminder of how precious ancient water truly is. More than 400 subglacial lakes lie hidden beneath Antarctic ice. Beneath the kilometers-thick ice sheet of Antarctica, scientists have discovered a hidden world of liquid water. More than 400 subglacial lakes have been identified so far, sealed away from the atmosphere above by enormous weight of ice. The largest of these, Lake Vostok, lies beneath nearly 4 kilometers of ice and has an area comparable to Lake Ontario. These lakes remain liquid because of geothermal heat rising from the Earth's interior and the insulating effect of the ice above, which traps enough warmth to keep the water just above freezing. Some of these lakes have been isolated from the outside world for millions of years, leading scientists to wonder whether they might harbor unique microbial life that has evolved in complete darkness and under immense pressure. Exploring these lakes requires drilling through kilometers of ice without contaminating the pristine water below, a challenge that pushes the boundaries of engineering. It is remarkable that liquid water can exist in one of the coldest places on Earth, hidden just beneath the surface. There may be more water locked in Earth's mantle than in all the oceans combined. Deep beneath the surface, hundreds of kilometers below your feet, water exists in a form you might not expect. It is not pools or underground rivers, but water locked within the crystal structure of minerals under tremendous heat and pressure. A mineral called ringwoodite, found in the transition zone of the mantle between roughly 400 and 700 kilometers deep, can hold significant amounts of water within its atomic lattice. Studies of seismic waves passing through this zone suggest that the amount of water stored there may equal or even exceed the total volume of all the surface oceans. This deep water never flows as a liquid. Instead, it is chemically bound within rock, released only when geological processes bring it closer to the surface through volcanic activity. The discovery has changed our understanding of Earth's water budget, revealing that the planet's interior may be far wetter than anyone previously imagined. It is a hidden ocean that you will never see, quietly influencing the geology of the world above. The ocean covers more than 70% of Earth's surface. From space, Earth appears overwhelmingly blue, and this is because the ocean covers more than 70% of its surface. This single, continuous body of water stretches from pole to pole, connecting every continent and island on the planet. It is divided by convention into distinct named regions: the Pacific, Atlantic, Indian, Southern, and Arctic, but in reality, it is one enormous interconnected pool. The Pacific alone is so vast that it covers more area than all of the world's landmasses combined. The ocean's sheer size means it plays a dominant role in almost every aspect of the Earth system. It absorbs the majority of the sun's energy that reaches the surface, stores heat, and distributes it around the globe through its currents. It produces roughly half of the oxygen we breathe through the photosynthesis of marine plants and phytoplankton. And yet, despite its immense influence on our lives, most people live their entire existence without spending much time on or in the open sea. More than 80% of the ocean remains unexplored. Despite the fact that the ocean makes up the majority of our planet's surface, we have explored remarkably little of it. Current estimates suggest that more than 80% of the ocean floor has never been mapped, observed, or visited by humans. We have more detailed maps of the Moon and Mars than we do of our own sea floor. The sheer depth and darkness of the ocean make exploration extraordinarily difficult. Below a few hundred meters, sunlight fades entirely, and the pressure mounts with every meter of descent. Submersibles capable of reaching the deepest trenches are rare and expensive to operate. Remotely operated vehicles have expanded our reach, but they can only cover small areas at a time. What we have found in the explored portions, bizarre creatures, underwater volcanoes, and mineral-rich hydrothermal fields, suggests that the unexplored regions hold wonders we can barely imagine. The ocean remains Earth's last great frontier, a vast expanse of mystery lying just beneath the waves. Ocean currents form vast rivers of moving water that influence global climate. Beneath the surface of the ocean, enormous rivers of water are constantly on the move. These are ocean currents, and they circulate heat, nutrients, and dissolved gases around the planet on a scale that dwarfs any river on land. Surface currents are driven largely by wind, while deep currents are set in motion by differences in water temperature and salinity, a process known as thermohaline circulation. Together, these currents form a vast conveyor belt that moves warm water from the tropics toward the poles and cold water back toward the equator. This redistribution of heat has a profound effect on global climate. The Gulf Stream, for example, carries warm water from the Caribbean across the Atlantic. keeping the climate of Western Europe much milder than it would otherwise be at those latitudes. If these currents were to slow or shift, the consequences for weather patterns, agriculture, and ecosystems could be dramatic. The ocean's quiet circulation is one of the most powerful forces shaping life on Earth. The Challenger Deep in the Mariana Trench is the deepest point in the ocean. In the western Pacific Ocean, the Mariana Trench plunges to a depth of nearly 11 kilometers below the surface. At its lowest point, known as the Challenger Deep, the ocean floor lies further below sea level than the summit of Mount Everest rises above it. The trench was formed by the collision of two tectonic plates, where the older, denser Pacific Plate is being forced beneath the smaller Mariana Plate in a process called subduction. The first crewed descent to the Challenger Deep was made in 1960 by Jacques Piccard and Don Walsh aboard the bathyscaphe Trieste. More than 50 years later, filmmaker James Cameron made a solo dive in a specially built submersible. Even at these crushing depths, life persists. Tiny shrimp-like amphipods and delicate, translucent organisms have been found on the trench floor, thriving in conditions that would destroy most human-made equipment. The Challenger Deep is a reminder that even the most extreme corners of the ocean are not beyond the reach of life. Pressure at the bottom of the ocean exceeds 1,000 atmospheres. At the surface of the ocean, you experience 1 atmosphere of pressure, the weight of the entire column of air above you. But for every 10 meters you descend into the water, the pressure increases by roughly 1 additional atmosphere. At the bottom of the Mariana Trench, nearly 11 kilometers down, the pressure exceeds 1,000 atmospheres. That is equivalent to having the weight of about 50 jumbo jets stacked on top of every square meter of your body. Under such forces, air spaces collapse, metal deforms, and most structures designed for the surface would be crushed in an instant. Yet life has adapted to these conditions. Deep-sea organisms have evolved flexible cell membranes and specialized proteins that function under enormous pressure. Their bodies contain no gas-filled spaces, so there is nothing to compress. Submersibles designed to reach these depths must be built from extraordinarily strong materials and engineered to withstand forces that are difficult to recreate even in the most advanced laboratory. The deep ocean is a world where pressure is the defining feature of existence. Despite crushing pressure and darkness, life thrives in the deepest trenches. You might expect the deepest parts of the ocean to be barren wastelands, devoid of life. But the reality is far more surprising. Even at the bottom of the Mariana Trench, organisms have been found living in complete darkness under pressures that would flatten most human-made structures. Tiny amphipods, single-celled foraminifera, and various species of bacteria have been collected from the deepest sediments. These creatures survive by feeding on organic matter that drifts down from the sunlit waters above, a slow rain of dead plankton and other debris known as marine snow. Some deep trench bacteria derive energy from chemical reactions rather than sunlight, feeding on hydrogen and sulfur compounds present in the sediment. Life in the trenches moves slowly and quietly. Growth rates are low, reproduction is sparse, and the organisms are often small and soft-bodied. Yet they are there, persisting in conditions that were once thought impossible. The deep trenches are living proof that life finds a way, even in the most extreme environments the Earth has to offer. Hydrothermal vents release superheated mineral-rich water on the ocean floor. Scattered along the mid-ocean ridges where tectonic plates pull apart, cracks in the sea floor allow cold ocean water to seep deep into the crust. As it descends, this water is heated by the magma below, sometimes reaching temperatures of over 350 degrees Celsius. Despite being far above the normal boiling point, the immense pressure at these depths keeps the water in liquid form. As it rises back toward the surface, it dissolves minerals from the surrounding rock, emerging from the sea floor as plumes of scorching, mineral-rich fluid. Where these plumes meet the frigid ocean water, the dissolved minerals precipitate out and build up towering chimney-like structures. The dark plumes from some of these vents, rich in iron and sulfur, have given them the name black smokers. The lighter ones, carrying different minerals, are called white smokers. These vents support entire ecosystems that thrive without sunlight, relying instead on the chemical energy carried by the hot water from below. Life may have originated around hydrothermal vents in the deep sea. One of the most compelling theories about the origin of life on Earth places it not in a warm, shallow pond, as was once commonly imagined, but in the darkness of the deep ocean near hydrothermal vents. These vents provide a steady supply of chemical energy, warmth, and dissolved minerals, all of the ingredients that the earliest chemical reactions of life would have needed. The porous mineral structures around the vents could have served as natural laboratories, hosting reactions between simple molecules and gradually producing more complex organic compounds. Over time, these compounds may have assembled into the first self-replicating molecules, the ancestors of all life on Earth. The hypothesis is supported by the fact that some of the most ancient branches of the tree of life are occupied by heat-loving microbes closely related to organisms found at modern hydrothermal vents. If this theory is correct, then the very first spark of life on Earth occurred in the deep, dark, pressurized waters of the ocean floor, far from the sunlight that most life now depends upon. Ocean waves transfer energy across vast distances, while water stays mostly in place. Watching waves roll toward the shore, it is natural to assume that the water itself is traveling forward. But in reality, ocean waves are primarily a transfer of energy, not of water. Each molecule of water moves in a roughly circular path as a wave passes through, rising and falling, but returning more or less to where it started. It is the energy that moves forward, passing from one group of molecules to the next, like a ripple through a crowd. This is why a floating object bobs up and down as waves pass, but does not drift significantly toward the shore until the waves break in shallow water. Waves are generated by wind blowing across the surface, and the stronger and more sustained the wind, the larger the waves become. Energy injected into the ocean by a storm can travel thousands of kilometers across open water before it finally reaches a distant coast. The wave that gently laps at your feet on a calm beach may have begun its journey far out at sea, carrying the memory of a storm you never saw. Swells can travel thousands of kilometers before breaking on distant shores. When a powerful storm churns the surface of the open ocean, it generates waves of many different sizes and speeds. As these waves move away from the storm, the longer, more energetic ones pull ahead, while the shorter, choppier ones fall behind. Over hundreds and thousands of kilometers, this sorting process produces the long, smooth, evenly spaced waves known as swells. Swells can cross entire ocean basins, traveling from storms in the Southern Ocean all the way to the beaches of California or Western Europe. Along the way, they lose very little energy because the deep water beneath them offers almost no resistance. Surfers often track distant storms to predict when the best swells will arrive at their favorite breaks. The swells that provide perfect surfing conditions on a sunny afternoon may have been born in a ferocious gale thousands of kilometers away days earlier. It is a beautiful example of how energy can be carried gently and silently across the vastness of the sea, arriving as a calm, rhythmic pulse on a faraway shore. Tides are caused by the gravitational pull of the moon and the sun. Twice each day in most coastal areas, the sea rises and falls in a slow, rhythmic motion called the tide. This eternal pulse is driven primarily by the gravitational pull of the moon. Although the moon is much smaller than the sun, it is far closer to Earth, so its tidal influence is about twice as strong. The moon's gravity pulls on the side of the Earth facing it, creating a bulge of water. At the same time, on the opposite side of the planet, inertia creates a second bulge. As the Earth rotates, coastal areas pass through these bulges and experience the rise and fall of the tide. The sun also contributes to the tides. When the sun and moon align during new and full moons, their combined pull produces the especially high and low spring tides. When they are at right angles, the neap tides are more subdued. Tides shape coastlines, drive nutrient-rich currents through estuaries, and provide habitats for countless marine organisms in the zone between high and low water. Gravity also creates tiny tides in the solid rock of Earth's crust. The tidal forces of the moon and sun do not act only on the oceans. They also pull gently on the solid body of the Earth itself. As a result, the ground beneath your feet rises and falls by a small amount with each tidal cycle. On average, this solid Earth tide moves the surface up and down by roughly 20 to 30 centimeters, though the motion is so smooth and so slow that you would never feel it. Scientists measure these movements with extremely sensitive instruments called gravimeters and tiltmeters. The solid tides have practical consequences for precision science. Particle accelerators and laser interferometers must account for the slight deformation of the crust to maintain their accuracy. Even GPS satellites factor in solid Earth tides when calculating positions. The idea that the apparently unyielding rock beneath us flexes gently under the pull of the moon is a humbling one. It is a reminder that nothing on Earth is truly rigid, and that the influence of gravity reaches even into the stone. Even the atmosphere experiences slight bulges of tidal pressure. Just as the moon's gravity raises tides in the oceans and in the solid crust, it also pulls gently on the thin blanket of air surrounding the Earth. These atmospheric tides are extremely subtle, consisting of tiny pressure variations that ripple around the planet twice each day. They are far too small to feel or to affect the weather in any noticeable way, but they can be detected by sensitive barometers. Interestingly, atmospheric tides are influenced more by the sun than by the moon, because solar heating causes the atmosphere to expand on the sunlit side of the planet, creating a pressure bulge that moves with the sun. The moon's gravitational contribution to atmospheric tides is smaller but still measurable. Scientists study these tidal signatures to understand how the atmosphere responds to external forces and to refine models of atmospheric dynamics. It is a quiet and almost invisible phenomenon, but it connects the air you breathe to the same gravitational dance that lifts and lowers the oceans twice every day. Tidal forces have been slowly lengthening Earth's days over billions of years. The tides do more than move water. They gradually transfer energy between the Earth and the Moon, and one of the long-term effects of this exchange is that the Earth's rotation is slowly slowing down. Each tidal cycle dissipates a small amount of rotational energy as heat, mostly through friction between the moving water and the ocean floor. Over billions of years, this has lengthened the day by a significant amount. Early in Earth's history, a day may have lasted only about 6 hours. Today it is 24 hours, and in the distant future, days will be even longer. At the same time, the Moon is very slowly spiraling away from the Earth, gaining energy from the same tidal interaction. It moves outward by about 3 to 4 centimeters each year, a distance so small that it takes millions of years to become noticeable. The quiet rhythm of the tides is gently reshaping the relationship between the Earth and the Moon, one imperceptible moment at a time. The water cycle has operated continuously for billions of years. Water is never created or destroyed on Earth. It simply moves from one place to another in an endless loop known as the water cycle. Water evaporates from the surface of oceans, lakes, and rivers, rises into the atmosphere as vapor, condenses into clouds, and falls back to the surface as rain or snow. It then flows over and through the land, eventually returning to the ocean to begin the cycle again. This process has been running without interruption for roughly 4 billion years, since the first rains fell on the young Earth. The energy that drives the cycle comes from the sun, which heats the surface and causes evaporation. Gravity provides the return path, pulling rain down from the clouds and drawing rivers toward the sea. Along the way, water sustains every living thing it encounters, delivering nutrients, carrying waste, and moderating temperatures. The water cycle is the planet's circulatory system, a tireless loop that connects the atmosphere, the land, and the sea in a single, continuous embrace. A single water molecule might spend centuries frozen in a glacier before flowing again. The time a water molecule spends in any given part of the water cycle varies enormously. A molecule that evaporates from the ocean may spend about 10 days in the atmosphere before falling as rain. If it lands in a river, it might reach the sea within weeks. But if that same molecule falls as snow on a glacier, it could remain frozen for hundreds or even thousands of years before the ice melts and releases it. In the deep ocean, water circulates on timescales of centuries to millennia. In underground aquifers, molecules can be locked away for tens of thousands of years. This wide range of residence times means that the water flowing from your tap right now might include molecules that experienced the last ice age alongside molecules that were in a cloud just yesterday. The water cycle is not a single loop, but a network of overlapping journeys, each molecule following its own unique path through time and space. The water you drink today may have once fallen as rain on a dinosaur. Because water is endlessly recycled through the water cycle, the molecules in your glass tonight have been on a very long journey. The total amount of water on Earth has remained roughly the same for billions of years. This means the water that now fills your cup has passed through countless forms and places since it first arrived on the planet. Some of those molecules may have once been part of an ancient ocean where marine reptiles swam. Others may have fallen as rain on a forest where dinosaurs walked more than 65 million years ago. They may have been frozen in glaciers, carried by rivers, and evaporated from tropical seas dozens of times since then. Though individual molecules are far too small and too numerous to track, the mathematics of the water cycle makes it statistically almost certain that some of the water you drink has passed through a dinosaur at some point in its history. It is a curious and quietly amusing thought to carry to sleep. Evaporation from the ocean provides most of the water that falls as rain over land. The ocean is the primary source of the moisture that feeds rainfall around the world. When the sun heats the surface of the sea, water molecules escape into the atmosphere as vapor, leaving behind the salts and minerals dissolved in the ocean. This purified vapor is carried inland by winds, where it eventually cools, condenses into clouds, and falls as rain or snow. Roughly 86% of global evaporation occurs from the ocean's surface, making the sea by far the most important contributor to the atmospheric moisture budget. The remaining evaporation comes from lakes, rivers, soil, and the transpiration of plants. Without the ocean's vast surface area acting as a giant evaporation engine, rainfall over the continents would be dramatically reduced, and many of the world's rivers, forests, and agricultural regions would not receive enough water to sustain themselves. The ocean is not only a reservoir of liquid water, but the starting point for the atmospheric arm of the water cycle that delivers fresh water to land. Plants release water vapor through transpiration from their leaves. Every day, plants draw water from the soil through their roots, transport it up through their stems, and release it into the air as vapor through tiny pores on their leaves called stomata. This process is known as transpiration, and it accounts for a significant portion of the moisture in the atmosphere over land. A single large tree can transpire hundreds of liters of water per day during the growing season. Multiply that by the billions of trees in a forest, and the result is an enormous upward flow of moisture that helps to generate clouds and rainfall over the region. In tropical rainforests, transpiration is so intense that the forest effectively creates its own weather, recycling water back into the atmosphere faster than it can drain away. This moisture is then carried downwind, providing rainfall to areas that might otherwise be much drier. Transpiration also cools the leaf surface as the water evaporates, functioning much like sweating in humans. It is one of the most important links between the plant kingdom and the water cycle. Water carries nutrients from mountain tops to ocean floors. From the moment rain falls on a mountain peak, water begins a long journey downward, carrying with it the story of every rock and soil it touches. As it percolates through the ground and flows across the surface, it dissolves minerals and organic matter, transporting these dissolved nutrients downstream. Rivers carry this nutrient-rich water through valleys and plains, feeding the soils that support agriculture and the wetlands that harbor wildlife. Eventually, the water reaches the ocean, where it delivers its cargo of dissolved minerals to the sea. In the ocean, these nutrients support the growth of phytoplankton, tiny organisms that form the base of the marine food web and produce a significant share of the world's oxygen. Even on the deepest ocean floors, the slow rain of organic particles from above delivers nutrients to the creatures of the abyss. Water is the thread that connects the highest land to the lowest sea, a single liquid carrying the chemistry of life from one end of the planet to the other. Over geological time, rainfall has shaped the face of the earth. The landscape you see around you, from gentle rolling hills to deep river valleys, has been sculpted primarily by water. Over millions of years, rainfall erodes rock, dissolves minerals, and carries sediment downstream, steadily reshaping the surface of the earth. Mountains are worn down grain by grain. Valleys are carved deeper with every storm. Coastlines advance and retreat as waves and currents redistribute sand and clay. Even the flattest plains owe their form to ancient floods and the slow deposition of waterborne sediment. The Grand Canyon, the fjords of Norway, and the limestone karst landscapes of Southeast Asia are all monuments to the patient work of water over geological time. This process is still happening right now. Every raindrop that strikes the ground loosens a few particles of soil. Every stream that flows after a downpour carries a bit more of the land toward the sea. Water does not carve quickly, but it never stops, and over the vast stretches of deep time, its cumulative effect is beyond anything human engineering could achieve. Lakes in temperate climates turn over twice each year, mixing nutrients throughout. In temperate regions, many lakes undergo a fascinating seasonal process known as turnover. During summer, the surface water is warmed by the sun and becomes lighter than the cooler water below, creating distinct layers that resist mixing. As autumn arrives and the surface cools, this temperature difference disappears, and the water throughout the lake reaches a roughly uniform density. Wind can then mix the entire lake from top to bottom, circulating nutrients from the deep sediments up to the surface and carrying oxygenated water down to the depths. A similar turnover occurs in spring, after the winter ice melts and the surface water warms back to the temperature of the deeper layers. These twice-yearly mixing events are vital for the health of the lake. They bring buried nutrients into the reach of sunlight, fueling blooms of algae and phytoplankton that support the entire food web. Without turnover, deep lakes could become stagnant, with oxygen-starved depths unable to support most forms of life. Because water is densest, just above freezing, lake ice forms at the surface first. The fact that water reaches its maximum density at about 4 degrees Celsius has a direct and life-preserving consequence for lakes. As autumn turns to winter, the surface water of a lake cools and sinks, being replaced by warmer water from below. This process continues until the entire lake reaches 4 degrees. After that, further cooling makes the surface water less dense, so it stays on top rather than sinking. When the temperature drops below freezing, ice forms at the surface and floats there, creating a solid lid over the lake. Beneath this lid, the water remains liquid at around 4 degrees, providing a livable environment for fish, amphibians, and invertebrates throughout the winter. If water did not have this unusual density behavior, the coldest water would always sink, and lakes would freeze from the bottom up. The entire aquatic ecosystem of temperate and polar freshwater habitats depends on this one peculiar property. It is a detail so small it might go unnoticed, yet it has shaped the evolution of freshwater life for hundreds of millions of years. Some lake bottom waters have remained unmixed for thousands of years. While most temperate lakes undergo seasonal turnover, some deep lakes are so sheltered or so uniquely layered that their bottom waters have not mixed with the surface for extraordinarily long periods. These are called meromictic lakes, and their deep layers can remain isolated for thousands of years. The separation is usually maintained by a strong density difference between the upper and lower layers, which may be caused by differences in salinity, temperature, or dissolved gases. In some meromictic lakes, the bottom water is rich in hydrogen sulfide and devoid of oxygen, creating conditions that are hostile to most life, but perfect for certain specialized bacteria. Sediments in these lakes accumulate in undisturbed annual layers called varves, which scientists read like tree rings to reconstruct past climates and environmental conditions. The stillness of the deep water in these lakes is almost eerie, a pool of ancient liquid sitting quietly below the light and life of the surface. They are among the most stable and unchanging environments on the planet. Rivers constantly reshape the land through erosion and sediment deposition. A river is not a fixed feature of the landscape. It is a living, moving force that continuously alters the ground through which it flows. On the outer curves of its bends, the faster-moving water erodes the bank, carving deeper into the land. On the inner curves, where the flow is slower, sediment is deposited, building up new land. Over time, this process causes rivers to meander, snaking across their floodplains in ever-changing loops. When a river floods, it spreads sediment across the surrounding plain, enriching the soil and creating some of the most fertile agricultural land on Earth. River deltas, where waterways meet the sea, are built entirely from sediment deposited over thousands of years. The Nile Delta and the Ganges Delta are among the most densely populated places on the planet, sustained by the nutrient-rich soil delivered by their rivers. Erosion and deposition are two sides of the same coin, a never-ending exchange of material between the land and the water that shapes every valley and coastline on Earth. Europa may contain more liquid water beneath its ice than all of Earth's oceans. Europa, one of the 4 large moons of Jupiter, is one of the most intriguing bodies in the solar system. Its surface is covered by a smooth shell of ice, crisscrossed by a web of reddish-brown lines that scientists believe are cracks in the frozen crust. Beneath this icy exterior, evidence strongly suggests the presence of a global ocean of liquid water, kept from freezing by the tidal heating generated by Jupiter's enormous gravitational pull. Models indicate that this hidden ocean may contain 2 to 3 times as much water as all of Earth's oceans combined. The implications are extraordinary. Liquid water is one of the key ingredients for life, as we know it. And if Europa's ocean is in contact with a rocky sea floor, chemical reactions similar to those at Earth's hydrothermal vents could be occurring in the darkness below. Space agencies are developing missions to study Europa more closely, with the hope of one day determining whether this distant moon harbors the conditions for life beneath its frozen surface. Enceladus shoots geysers of water ice into space through cracks in its surface. Enceladus, a small moon of Saturn barely 500 kilometers across, has become one of the most exciting targets in the search for life beyond Earth. In 2005, the Cassini spacecraft observed dramatic plumes of water ice and vapor erupting from long cracks near the moon's south pole, known informally as tiger stripes. These geysers shoot material hundreds of kilometers into space, and some of it falls back to the surface, while the rest drifts away to feed Saturn's faint E-ring. Analysis of the plume material revealed not only water, but also salts, silica particles, and simple organic molecules, all signs consistent with a warm, salty ocean beneath the ice crust. The silica particles in particular suggest that hot water is interacting with rock on the ocean floor, a process reminiscent of hydrothermal vents on Earth. Enceladus is essentially sampling its own hidden ocean and ejecting the evidence into space, giving scientists a rare opportunity to study an extraterrestrial sea without even needing to land. Mars once had flowing water that carved channels and lake beds still visible today. The surface of Mars is now a cold, dry desert, but it was not always so. Billions of years ago, water flowed freely across the Martian landscape, carving river channels, filling lake basins, and possibly even forming a shallow ocean in the northern lowlands. Orbital images reveal dry river valleys hundreds of kilometers long, layered sediments deposited in ancient lake beds, and mineralogical evidence of clays and salts that can only form in the presence of liquid water. Rovers on the surface have confirmed these findings, examining rocks that show clear signs of past water interaction. The Jezero crater, where the Perseverance rover landed, was once a lake fed by a river delta, and its sediments may preserve traces of ancient microbial life, if any ever existed. What happened to all that water is still a subject of active research. Some escaped to space as the planet's atmosphere thinned, while some remains frozen underground and at the poles. Mars is a quiet testament to how dramatically a world can change when its water disappears. The polar caps on Mars contain water ice mixed with frozen carbon dioxide. Both poles of Mars are capped with bright white deposits that grow and shrink with the Martian seasons. These polar caps are made of two components. The permanent layer beneath consists of water ice, sometimes kilometers thick. On top of this sits a seasonal layer of frozen carbon dioxide, or dry ice, which condenses from the thin Martian atmosphere during winter and sublimates back into gas during spring. The seasonal caps can extend far toward the equator during the Martian winter, then retreat dramatically as the hemisphere warms. The northern polar cap is slightly larger and contains more water ice, while the southern cap retains a thin layer of carbon dioxide ice year-round. Together, the polar caps represent one of the largest known reservoirs of water on Mars, though accessing it would present enormous engineering challenges. If the water ice in the Martian poles could somehow be melted, it would cover the entire planet in a shallow layer of liquid. The poles of Mars are frozen archives of the planet's watery past. Venus may have had oceans that boiled away in a runaway greenhouse effect. Venus today is an infernal world, with surface temperatures hot enough to melt lead and an atmosphere thick with carbon dioxide and sulfuric acid clouds. But some scientists believe it may not have always been this way. Computer models suggest that early Venus could have had moderate temperatures and liquid water on its surface, possibly for hundreds of millions of years. If this is true, something went catastrophically wrong. As the young sun grew brighter, temperatures on Venus began to rise, increasing evaporation. The additional water vapor in the atmosphere trapped even more heat, raising temperatures further and evaporating still more water. This vicious cycle, known as a runaway greenhouse effect, may have eventually boiled away all of Venus's oceans and left the water vapor in the upper atmosphere, where solar radiation split the molecules and the hydrogen escaped into space. Venus is a cautionary example of what can happen when the delicate balance between water and temperature tips too far. It stands as a stark reminder of just how fragile the conditions for liquid water truly are. Earth slowly loses water to space as hydrogen escapes from the upper atmosphere. Although we tend to think of Earth's water supply as permanent, the planet is actually losing water to space at a very slow rate. High in the upper atmosphere, ultraviolet radiation from the sun can split water molecules into hydrogen and oxygen. The lightweight hydrogen atoms, being the smallest and fastest moving particles, can reach escape velocity and drift away into space. This process, known as atmospheric escape or hydrogen loss, has been occurring since the Earth first had water. Over billions of years, the total amount lost is thought to be modest compared to the vast volume of water on the planet, but it is not zero. Mars likely lost much of its water through a similar process after its protective magnetic field weakened. Earth's strong magnetic field and its thicker atmosphere help to slow the rate of hydrogen escape, but they do not stop it entirely. It is a gentle and almost imperceptible loss, a few kilograms of hydrogen drifting away into space each second, barely noticed against the vastness of the oceans below. Astronomers detect water vapor on distant exoplanets by analyzing starlight. When a planet passes in front of its host star, as seen from Earth, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. By carefully analyzing the wavelengths of light that are absorbed during this transit, astronomers can identify the chemical composition of the planet's atmosphere. Water vapor has a distinctive absorption signature that shows up clearly at infrared wavelengths, and it has been detected in the atmospheres of several exoplanets orbiting distant stars. The James Webb Space Telescope has greatly enhanced our ability to make these measurements, revealing water on worlds that are dozens or even hundreds of light years away. Detecting water is particularly exciting because it is considered one of the key prerequisites for life as we understand it. However, the presence of water vapor alone does not mean a planet is habitable. Many of these worlds are scorching gas giants with no solid surface. Still, each detection adds to the growing evidence that water is widespread in the universe. Deep water appears blue because it absorbs red light more effectively. If you fill a glass with pure water, it looks clear and colorless. But in large quantities, water takes on a distinct blue hue. This is not because it reflects the sky, as many people assume, but because water actually absorbs red light more readily than blue light. When sunlight enters the ocean, the longer red wavelengths are absorbed within the first few meters, while the shorter blue wavelengths penetrate much deeper. As you descend further, even the blue light fades until below about 1,000 meters, there is complete darkness. The blue color you see in a swimming pool, a deep lake, or the open ocean is the result of this selective absorption. The effect becomes visible only when there is enough water for the difference in absorption to accumulate. In very deep or very clear water, the blue can be strikingly vivid. It is a subtle optical property that paints the ocean in the most calming of colors, turning the world's largest body of water into a vast, serene expanse of blue. Pure water can glow faintly under ultraviolet light. Under normal conditions, pure water is virtually colorless and transparent. But when exposed to short-wavelength ultraviolet light, water molecules can absorb the energy and re-emit it at slightly longer wavelengths, a process known as fluorescence. The glow is extremely faint and is not visible to the naked eye under ordinary circumstances, but sensitive instruments can detect it. Researchers use this property in laboratory settings to study the purity of water samples, since dissolved organic matter fluoresces much more strongly than pure water itself. In environmental science, the fluorescence of natural water samples can reveal the presence and concentration of organic pollutants, algae, and other biological material. The glow is caused by the electronic transitions within the water molecule when it absorbs ultraviolet photons and quickly releases the energy as visible or near-visible light. It is one of those quiet properties of water that most people never encounter, but it serves as a useful scientific tool and a reminder that even the most familiar substance can behave in unexpected ways when probed with the right kind of light. Bioluminescent plankton make ocean waves glow blue-green at night. On certain warm evenings, the crests of waves along tropical and temperate coastlines light up with an ethereal blue-green glow. This magical display is caused by bioluminescent plankton, tiny marine organisms that produce light through a chemical reaction within their cells. The most common of these organisms are dinoflagellates, single-celled creatures that flash when disturbed by the movement of water. Each flash lasts only a fraction of a second, but when millions of them are triggered at once by a breaking wave or the stroke of an oar, the combined effect is breathtaking. The light is produced by a molecule called luciferin reacting with an enzyme called luciferase in the presence of oxygen. Scientists believe the purpose of the flash is to startle or deter predators, though the exact benefit varies between species. Beaches known for bioluminescence attract visitors from around the world, drawn to the surreal sight of glowing water beneath the stars. It is one of the most enchanting encounters between water and life on our planet. Sound travels nearly 4 times faster through water than through air. In air, sound waves move at roughly 340 meters per second. In water, they travel at nearly 1,500 meters per second, almost 4.5 times faster. This dramatic difference is due to the fact that water is much denser and less compressible than air. Sound waves are essentially vibrations passed from one molecule to the next, and in a denser medium where molecules are already close together, those vibrations are transmitted more efficiently. The speed of sound in water also varies with temperature, salinity, and depth. Warmer water and higher salinity both increase the speed, while deeper, cooler water slows it down until the increasing pressure reverses the trend. At a certain depth, these competing effects create a channel where sound can travel extraordinary distances with very little energy loss. This deep sound channel has been used by the military to detect distant submarines and by scientists to monitor underwater volcanic activity. It is also the highway through which whales send their songs across entire ocean basins. Whales communicate across entire ocean basins using low-frequency calls. The deep ocean is not a silent world. It is filled with sounds, and among the most remarkable are the calls of large whales. Blue whales and fin whales produce low-frequency vocalizations that can travel thousands of kilometers through the water. These calls are often below the range of human hearing, rumbling through the deep sound channel at frequencies as low as 10 to 20 hertz. The calls serve a variety of purposes, including attracting mates, maintaining contact with distant group members, and possibly navigating by listening to echoes from underwater features. Before commercial whaling reduced their numbers, whale songs would have filled the ocean with a continuous background of sound. Even today, hydrophones placed on the ocean floor pick up whale calls from animals hundreds or thousands of kilometers away. The ability to communicate across such vast distances is made possible by the remarkable sound-carrying properties of water. It is a humbling thought that beneath the surface of a seemingly quiet sea, conversations are taking place that span entire oceans. Every living organism requires water to survive. From the smallest bacterium to the largest whale, every known living organism depends on water for its survival. Water is the medium in which the chemistry of life takes place. It dissolves the molecules that cells need, carries waste products away, maintains the structure of cell membranes, and provides the environment for the countless chemical reactions that keep organisms alive. Even organisms that live in the driest deserts, such as certain lichens and tardigrades, require at least small amounts of water to carry out their basic metabolic processes. When water is unavailable, some of these creatures enter a state of dormancy, suspending their life functions until moisture returns. The search for life beyond Earth is, in many ways, a search for water, because wherever liquid water exists, the conditions for life may also exist. It is the one substance that unites all living things on our planet, from the deepest ocean vent to the highest mountain summit. Life and water are inseparable partners in the story of Earth. Some microbes survive in superheated water near boiling point. In the scalding waters around hydrothermal vents and hot springs, where temperatures reach or exceed 100 degrees Celsius, certain remarkable microbes thrive. These heat-loving organisms, known as thermophiles and hyperthermophiles, have evolved proteins and cell membranes that remain stable at temperatures that would destroy most other forms of life. Some of the most extreme examples can grow at temperatures above 120 degrees Celsius, surviving in water that would be superheated steam at normal atmospheric pressure. These microbes are found in hot springs like those in Yellowstone, in deep-sea vents, and in volcanic regions around the world. Many of them belong to the Archaea, an ancient domain of life that branched off very early in evolutionary history. Their existence pushes the boundaries of what we consider habitable, suggesting that life can adapt to conditions far more extreme than once thought. Studying these organisms informs the search for life on other planets and moons, where hot water and rock may provide similar environments. Without water, the carbon chemistry of life would collapse entirely. Carbon is often called the backbone of life, and for good reason. Its ability to form stable bonds with many other elements allows it to build the complex molecules that make up DNA, proteins, fats, and carbohydrates. But none of this chemistry would work without water. Water provides the environment in which these molecules are assembled, folded, and used. It participates directly in many of the reactions that build and break down biological molecules, including hydrolysis and condensation reactions that are central to metabolism. Water's polarity helps to organize molecules within cells, driving the formation of cell membranes and influencing the shapes of enzymes. Without water, proteins could not fold, DNA could not maintain its double helix, and the chemical reactions of metabolism would grind to a halt. Carbon provides the structural framework, but water provides the stage on which the entire drama of life is performed. Together, they form the foundation upon which every living thing, from a single-celled organism to a dreaming human, is built. And now, the quiet wonders of water begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the most essential substance on Earth. From the hydrogen atoms born in the first moments of the universe to the oxygen forged in dying stars, from the frozen comets that delivered water to our young planet to the hidden oceans beneath the moons of distant worlds. You have explored how water expands when it freezes, protecting life beneath winter ice. You have learned how surface tension lets insects walk on water, how capillary action lifts water to the tops of the tallest trees, and how the water cycle has been turning for 4 billion years without pause. You are connected to this story more deeply than you may realize. Right now, as you listen, water is doing what it has always done, flowing through your blood, cushioning your brain, carrying nutrients to every cell. It does not need your permission or your attention. It simply sustains, faithfully and silently, as it has since the very first moment of your life. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle fall of rain, like the quiet pulse of waves reaching the shore, like the slow drift of clouds across a summer sky. Tonight, as you rest, water continues its quiet work. It will circle the globe in currents you will never see. It will rise as mist and fall as dew. It will flow through rivers and seep through soil, and it will move through you as it moves through all living things. You are a small, warm presence within this vast liquid world, peacefully resting among the waters. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are never truly separate from the water that sustains all life, for it flows through you always, connecting you to oceans, clouds, and stars in ways you will never fully see. Thank you for joining me on this journey through the wonders of water. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of how our world works. There are more wonders waiting, more secrets hidden in the depths of seas and the quiet corners of nature, more gentle truths to drift through on quiet evenings. Rest well, and may the gentle flow of water carry you softly through the night. This has been Drowsy Discovery. Good night.